Okay, so let's look at rotating parity. It's a pretty simple idea. We're going to take our RAID 4, which is our basic parity-based system, and we're going to change it just a little bit. And well, the way we're going to change it is, instead of, to make sure that that one disk doesn't become the parity bottleneck, what we're going to do is we're going to rotate that parity. So let's say we put the parity for this stripe here, and let's say we put the parity for this stripe here, and so forth and so on. And you can see the parity then is rotated across here in some sort of repeating pattern. This is one way to do it. There's lots of different ways to do it. And that's going to be our basic RAID 5 technique. Everything else is identical to RAID 4. It's block-based parity. It just rotates the parity to avoid the parity disk bottleneck. So if we're going to evaluate that, this is going to be very quick. The capacity is going to be the same as RAID 4. The reliability is going to be the same as RAID 4. Reads, random reads, well, it changes a little bit. Why? Think about it. Let's say we're doing random reads. With RAID 4, we were generally only using 3 disks, 3 out of the 4, or D-1 disks. Here, we can distribute the reads to all the disks. So our random read bandwidth improves a little bit. Let's skip random writes for a second. Sequential reads and sequential writes actually stay the same. I'll leave it as an exercise to you to figure out why. But the biggest change is to random writes, because random writes now can happen in parallel. Let's say we're writing to 0 and 4 again. You can see 0 has to access disk 3 because we have to read and write this parity, and the update to 4 is going to have to read and write parity on disk 2. So even though each I/O still causes 4 physical I/Os, which means we're going to have a D over 4 kind of scaling rule for the bandwidth, we're going to scale with the number of disks, which is critically important. Before, with the RAID 4, we were bottlenecked on the parity disk. Here, we get some parallelism out of the system. And the reason we divide by 4 is because, again, each logical I/O is doing 4 physical I/Os. There's no magic. When you have a lot of I/Os going on, you have to pay for each of them. Okay, so let's summarize a bit. RAID is terrific because it allows us to increase capacity. It allows us to increase performance. And it allows us to increase the reliability of the system as well. When people think about RAID systems, they generally think about, if they only care about performance and not about reliability, and maybe capacity, let's say, but not reliability, well then of course you'd always go with RAID 0 or striping. Very risky though. So what it means in reality is when people are talking about RAIDs, they tend to be talking about RAID 1, mirroring, or RAID 5, parity. So that's the question. So let's look at the evaluation of each of those. This is RAID 5s. Let's go ahead and look at RAID 1s as well. And you can see here some of the differences. Let me do it like this, in fact. Here's RAID 5, and let me put RAID 1 over here. So what are we going to have here? So if we're comparing the two of them, what we can see here is some obvious differences. One of the major differences is in capacity. Parity-based techniques give you a lot more of the capacity that you paid for. You paid for all those disks. With RAID 5, you can use most of them for user data. With mirroring, you get half of the data. So that's painful. In terms of reliability, Well, they both tolerate a single failure for sure, so they're kind of similar along those lines. Now, in terms of performance, well, there's some subtleties. Random reads, they both do well, scaling with a number of disks. Sequential I/O, well, parity-based techniques do better because mirroring tends not to do so well. The major difference and the place where RAID 1 does better is on random writes. Though it gets half the bandwidth of, say, a stripe system, it does twice as well as any parity-based system based on RAID 5 because it's only doing 2 physical IOs for every logical IO, whereas something like RAID 5 is doing 4 physical IOs for every logical IO. So if you care about capacity, that's your major goal, RAID 5. If you care about sequential performance and you want the reliability again, which most people do, then it's RAID 5. But if you care about random writes, that's your major performance bottleneck, then you go with RAID 1. And this is common enough, like for example in database management systems or DBMSs, that'll be a common choice for people in that space because paying that factor of 2 penalty is much better than paying a factor of 4. You could think of that as to have equivalent performance, you'd have to buy twice as many disks in a RAID 5 system. So that's RAID. There's a lot more to learn there, thousands of papers you could read about many different RAID techniques. For example, there's RAID 6 where you might have 2 parity disks. There's techniques that people use in high-end systems based on checksums to guard against all sorts of other disk failures. All those things are interesting, worth looking at perhaps, but in our simple evaluation, all we've looked at are basically some simple techniques like parity and mirroring, and hopefully that gives you some sense of how a modern RAID system is built.